Hello, Chem 1B. This is chapter 19, lecture video 4, and we're going to be talking about how to calculate the cell potential for a redox reaction, or the electromotive force for a redox reaction, or EMF for short. As we learned in the previous lecture video, in a spontaneous reaction, electrons are going to flow from the anode to the cathode, and this is due to the fact that the cathode has a lower electrical potential than the anode, meaning the cathode has a positive charge and the anode has a slightly negative charge, and so our electrons move from the anode to the cathode, drawn by that positive charge because electrons are negative. This difference in potential between the anode and the cathode is measured in units of volts. And for a 1 molar solution, under standard conditions, the standard cell potential is called E0 cell, and this is the cell potential for the entire voltaic cell. The whole redox reaction has this one value. And if it's positive, we have a spontaneous process. If it's negative, we have a non-spontaneous process. We can calculate our E0 cell from our standard reduction potentials. Standard reduction potentials, or E0 red, is the potential for a half reaction, specifically a half reaction. This part is very important, written as a reduction. So regardless of whether or not that half reaction is a reduction in our voltaic cell or not, we use standard reduction potentials to calculate the E0 cell. And when we're looking these up, the half reaction that we're going to be looking at may be the opposite because they're all always written as reductions, regardless of whether that's what's actually happening in your reaction. All right, so let's talk about that. These are cell potentials, or half cell potentials. It's the potential for a half reaction written as a reduction. Now, how do we measure that? Well, we have to have a kind of standard to measure them against, and that standard is known as the SHE, or the standard hydrogen electrode, SHE, abbreviated often as SHE. The SHE is what we call a reference electrode. So the way we measure all of these standard reduction potentials here is by putting them together with a voltaic cell where SHE is the anode and the one we want to measure is the cathode. We define the reduction potential for the SHE, or the standard hydrogen electrode, as 0. And so if we put them together, we can measure the voltage coming out of that, and whatever that voltage is our standard reduction potential for the anode, or I'm sorry, the cathode. This is the reaction known as the SHE. We have to have 1 molar here so that we're at standard conditions, and 1 atmosphere here so that we're at standard conditions. And this is what's defined as 0 volts. And you should kind of have this reaction in the back of your head, because if I say, hey, we're doing a reaction with the SHE versus this, then you need to know that that's what I'm talking about. I will not tell you what the SHE reaction is. It's basically H2 or H plus going to H2 gas as a reduction. Now, we can't directly measure half reaction potentials because, well, if you don't have both halves of the reaction happening, you don't have the reaction happening. So that's why we use this method with the SHE as 0 as definition, and then we compare that to some other reaction at the anode. Sorry guys, that was my son. In this case, the cell voltage measured equals the reduction potential for the half reaction. And the way we calculate cell potential is this. We take the reduction potential of the cathode and subtract that from the reduction potential of the anode. Generally, these guys, we just need to look up the value for. All right, so let's continue on. Now, this equation I will provide on your tests or quizzes. Well, just your test, because we're not quizzing on chapter 18. So let's consider this oxidation reaction relative to the SHE. and we're going to make the SHE our cathode and compare it. Now, if the SHE is our cathode, that means that's this guy, and it has to be 0 volts because that's what the SHE is defined as having for its reduction potential. That means this is my zinc solid going to zinc 2 plus 2 electrons. Now, so if I go away and I actually measure the cell potential here, I'm going to get this value if you actually did it. Now, what that means is this guy would have been measured if we were actually doing this. We're trying to determine an unknown cell standard reduction potential. Then we'd measure the cell potential just by putting a voltmeter on our cathode or our voltaic cell. And we could read that off. Then we go, hey, there's my She. It's the cathode. Here's my anode. And since this is a positive value, that means this value must have been negative. We can just rearrange. We get that the standard reduction potential for this zinc reaction is negative 0.67 volts. Now, wait a second. This is an oxidation. Why are we talking about standard reduction potentials? It doesn't matter. We still use the reduction potential, right? We know that it's an oxidation because it's occurring at the anode, but we're still going to look up the standard reduction potential when using this equation. So if we rewrote this as a reduction, this is how we would find it in like a table of standard reduction potentials is, hey, zinc 2 plus is going to zinc solid because it's a reduction. But I know that I'm actually doing the opposite of this in my reaction because that's what I was told. I was told the zinc solid is happening at the anode. So then we just flip it, but we wouldn't change the sign of this guy because we want this value here. Kind of tricky. So you got to remember that it's always going to be written as a reduction. And we can look this up most of the time. Okay, so here's a picture of that redox cell that we just talked about, where this guy on this side is our SHE. You can see this is our platinum electrode, our inert electrode here. And you can see that as the H plus is being reduced, it forms hydrogen gas. It bubbles up into this container. We're trying to make sure we keep that hydrogen gas at an atmospheric pressure of 1 because of standard conditions. And then, the zinc is being oxidized. These positive ions go up this way. These negative ions come in so that everything kind of stays the correct charges. The same thing over here. Negative charge going up, positive charge going down. We get our voltage that we saw. And this is kind of a general setup of how you might measure a standard reduction potential against the SHE. So here's just a big list of standard reduction potentials. You can see that all of these reactions here are reductions. That's like kind of by definition. And I would provide something like this on your test for exam 3. Probably a longer list actually, and then you just need to kind of find the correct values, correct redox reactions that are occurring. Use whichever value here that you think in our E naught cell reduction cathode minus E naught reduction anode type equation. All right, so let's continue on. Again, reduction is the key word here. These are all going to always be written as reductions, and it does not matter if you don't have this occurring as a reduction, you have it as an oxidation. We're still going to use this value when we plugged into that equation. So one thing to kind of think about is that anytime you have an E naught reduction that's greater than 0, that will be spontaneous reductions relative to the SHE. In other words, this guy is being oxidized. The SHE is oxidized in this scenario. Whereas if E naught reduction is less, then the reduction of zinc 2 plus versus the oxidation of the SHE is not spontaneous, because we'll get a negative E naught cell. However, the oxidation of zinc is going to be spontaneous with the SHE. Basically, if you think about this, right, we have two equations here. E cell is equal to, again, the ugly E, the reduction potential of the cathode minus the reduction potential of the anode. And we know the reduction potential of the SHE, by definition, has a value of 0. And if this guy's being reduced, then it's happening at the cathode, which makes this guy happening at the anode. So if we think about that, that means this is our scenario here. E naught cell is equal to 0. Is equal to negative 0.76 minus 0, which gives me a negative 0.76 here, volts. Negative E naught cell, non-spontaneous. However, if we flip this reaction a little bit, right, if we're talking about here now, zinc is being oxidized with the SHE being reduced, so we'd have 0 volts minus negative 0.76 volts, which would give us positive 0.76 volts. So spontaneous in this scenario. Kind of gives you an idea of how this equation works a little bit, hopefully. One important thing about standard reduction potentials that we need to talk about is that stoichiometric coefficients do not affect the reduction potential. In other words, if I multiply this guy by 2, I still have the same reduction potential. So even though zinc 2 plus 2 electrons goes to zinc solid, has a reduction potential, if you look it up, of negative 0.76 volts. Doesn't matter. If you multiply it by 2, you still have the same value. This is different from S naught and delta H naught of formation and delta G naught of formation as like a standard value that we use. Okay, so let's say we want to calculate a cell potential or an E naught cell or an electromotive force or any of those words for a reaction. Let's say the reaction we want to do this for is aluminum solid reacting with I2 solid going to Al3 plus aqueous and I minus aqueous. This is not balanced, right? But actually, in order to find your E naught cell or your cell potential, you don't need to balance the reaction. You just need to identify what is being oxidized and what is being reduced. Now, some of the things we notice here is that aluminum is going from 0 oxidation number to 3 plus. That is an oxidation, and we know oxidation occurs at the anode. So I know that this is the half reaction occurring at the anode. If aluminum is oxidized, then the I2 must be reduced, right? Oxidation number of 0 here, going to negative 1, that's a reduction. So I know the half reaction occurring at the cathode, because at the cathode we have reduction, is this. These are the two half reactions. I need to go look up the E naught red values or the reduction potentials for. Now, I'm not going to find this reaction in a reduction potential table because this is an oxidation. What I am going to find, however, is that Al3 plus 3 electrons goes to Al solid. I'm going to find this reaction in the reduction potential. And I'm just going to use its value even though we have its opposite occurring. We're not going to flip the sign. We're going to keep it exactly the same as whatever I find that value for, and I'm going to use that. So if we go look up their respective reduction potentials, we get these two values. Now the next step here is just go, oh, hey, well, E naught cell is equal to, the reduction potential of the cathode minus the reduction potential of the anode. Well, great, here's my anode, so that goes there. Here's my cathode, that goes there. And I can hit equals. In other words, positive 0.54 minus a negative 1.66 gives me a positive 2.2 volts as my cell potential. And this is a positive value, so this redox reaction that I have here is spontaneous. All right, so we're going to stop this recording here. If you guys have any questions, let me know. I have office hours, or you can always email me as usual.